Hello everyone, my name is Ellis Fenske and I'm here to talk to you today about our paper, 3 years later, a study of MAC address randomization in mobile devices and when it succeeds. And this is joint work between the MITRE Corporation and the U.S. Naval Academy. So let's get started. By way of motivation, I just want to talk about location privacy in mobile devices. So mobile devices are everywhere, they're always in your pocket, they're often co-located with people as they move around. And they are constantly probing for Wi-Fi. So in this talk, we're just talking about Wi-Fi, no other wireless protocols. And so these probe requests tend to use persistent identifiers. In particular, we're interested in the MAC address, but also there are many others. And so we're interested in what are these mobile devices constantly sending out that reveal information about sort of their owner or their identity. And this is a serious tracking concern because you can follow devices as they walk around, as the people who own them walk around. And so industry has responded by implementing a technology called MAC address randomization, where when devices go to send probe requests, which are sort of constant, they don't use their hardware address, and instead they use a random address. So no one can tell which probe request belongs to which device, and they can't track anybody around. And so let's just look at the previous work for a moment. This is a follow-on paper. So in 2017, MAC address randomization had just been deployed very effectively on iOS, semi-effectively in Android. Some devices did it and some devices didn't. So there have been many recommendations and many improvements. So things are quite different now. And our goal was to update our previous results and try to understand sort of the current state of the mobile device landscape. And try to understand, well, is the old result still true? Probably not, but in which ways exactly? So we also had to change our methodology from previous work because the methodology had relied on collecting a bunch of probe requests in the wild and then doing some identifying and piecing things together to try to figure out what was going on in the mobile device universe. But privacy protections have gotten a bit better. That is much more difficult now. So we needed another approach, and our approach was individual tests. So we had a corpus of 264 mobile devices, and we did passive tests where we put one device at a time in this RF shielded enclosure and recorded on the 3 non-overlapping 2.4 gigahertz channels. And then we just waited until we saw enough probe requests or until 20 minutes passed. Some of these devices were very not talkative. And so we did this actually for three tests per device. We tested them in the action state while they were constantly being sort of stimulated with the robot. The screen was on, it's sort of simulating someone using them. We tested them in the idle state where they were just left alone, so to simulate being in a pocket or a purse. And then we also went into the Wi-Fi settings and physically turned Wi-Fi off to see if they were still sending out probe requests. And then we also performed active attacks on a subset of the devices, mostly modern devices. So let's talk about the experiments. First, we have a pretty broad range of manufacturers, focused primarily, though, on the manufacturers that produce most of the mobile devices that we sort of see in the wild in the United States. And we also have a pretty broad range of Android version, iOS version, and release year. I'll also mention that we updated these devices if we could. So we tested a lot of really older devices with the hopes that we could then update them and test them again to see if the privacy protections improve with the software update. And so that's why you see a lot of these older devices being tested as well. And so we found some surprising results. In fact, Android devices are really different from each other, as it turns out. Some of them will send their hardware address in probe requests while the Wi-Fi is turned off. So the user is trying to turn Wi-Fi off and keep them quiet. And instead, they are sort of insisting on broadcasting a permanent unique identifier. We found one device where when we applied a major Android version update, randomization stopped. So the privacy protections got worse. And there's many other sort of one-off strange behavior that you can see if you test hundreds of different Android devices. You can see the paper if you want to know more. The big takeaway from all of this, though, that I'm trying to get across is that if you have any question about sort of what's going on with mobile devices, the answer is, well, it depends on the device, more or less. So we have to look at trends, we have to look at patterns, we have to look at sort of how things are changing in the mobile device landscape, rather than sort of making categorical statements, because none of those will be correct entirely. So let's look at some of these features that allow sort of tracking in these probe requests. The first one is obviously the MAC address. And MAC addresses, as we talked about before, are random, but they're not equally random all in the same way. So in order to select a random address, the device has to sort of pick which bits to be random and which bits to be fixed, and sort of to design a scheme, a bitwise structure for how they draw these random addresses. And so we called that bitwise structure a MAC address scheme. And so the first scheme that we see is 46-bit randomization, and 2 of the bits in the MAC address have to be fixed, and randomizing the rest gives you 46-bit randomization. And that's what all iOS devices have always done, and it's what Android 10 devices are sort of doing now, and some Android 6 through 9 devices also have done it in the past too. So it's sort of emerging as the de facto standard. And I will say this randomizes the most bits possible, but that's not really strictly even necessary. Only randomizing half of these is going to give you enough sort of privacy and collision avoidance, I think. But, this seems to be the most common approach now in the modern era. But there are other approaches, especially if you just look maybe 1-2 years in the past. So here is DA-A119. This is one example of what we call a prefix scheme, where you fix a prefix, which is some number of bits or bytes, and then you randomize the rest. And so we call this one DA-A119 because those are the bytes that are fixed, the first 3. This is a Google CID. The remaining 3 are random in this scheme, and this is Android 6 through 9, so pretty much gone on Android 10. You upgrade a device to 10, and this will stop, usually. And many manufacturers use this, so not just Google phones, but phones from many manufacturers. The second one we saw was 926AC3, which is the Motorola Nexus 6. We only saw one device do this. It's the only one we ever saw do it, but that's is another scheme that we saw in the wild and in our lab. And the next one we saw was much more common, which was sort of a more generic Motorola scheme. And actually, this scheme is kind of sort of properly a class of schemes, because the scheme says to take the hardware MAC address of the Motorola device, and then that hardware MAC address has an OUI, and that OUI is the fixed prefix. So it fixes the OUI of the device that is sending these messages, and then randomizes the rest. So you can actually sort of tell a couple of Motorola devices apart, maybe, using this scheme, because they have different OUIs. And the next one we saw was new. It was O2. So the O2 scheme just fixes that first byte and randomizes the rest. And this was deployed on Samsung, Android devices 7 through 9. Not all Samsung devices, but many of them on these operating systems do. But if you take Samsung device and you upgrade it to Android 10, start doing 46-bit randomization instead. Right, so it's sort of older Samsung devices of a certain class, which actually allows you to learn a lot about what kind of device is sending these probe requests if you see this address. And then this is not really a randomization scheme proper, but just for completeness, we have the hardware address. Some devices just use their hardware address all the time, and that's Android 6 through 9, phased out in Android 10. And so not only is the bitwise structure of these addresses change from manufacturer to manufacturer and OS to OS, we also saw that the time at which sort of the random address and the hardware address are used, the consistency of the randomization is different, sort of within a device based on the state and behavioral characteristics, and also between devices. So lots of variation. And some devices we noticed will change their behavior between the active state and the idle state. So those tests that we did, the action state and the idle state, were something that we invented based on guesses, because we suspected that this might be happening. Right? That devices will actually change their RF emissions, their Wi-Fi emissions, based on whether or not a user is touching them. And that's true for some devices. Not all devices, but some devices. Right? They'll stop randomizing when they become activated, when a user touches them or turns the screen on. Some devices will sort of send out their hardware address in between random addresses and just sort of, usually be randomizing and then just decide to send the hardware address in between for whatever reason, maybe for fun. And then we also, we had to classify these sort of strange behaviors. And so we have sort of 4 broad classification bins that we invented. The first one is always, where devices consistently use their random address all the time. Second is idle, where you have consistent random addresses, but only while the device is left alone. So if you use it, it will at least some of the time start using the hardware address. And that at least gives you sort of peace of mind if the device is stuck in your pocket and you don't use it, that it's not sort of broadcasting a persistent permanent identifier. And then we have mixed, which is to say we couldn't really identify behavioral characteristics that would make these devices do whatever they did, but this is rotation, right? So they both used random addresses and hardware addresses, but not in any discernible sort of pattern. Often it would be sort of rotating back and forth between the two in a given state. And then for never, this is just devices that never used random addresses and always use the hardware address. So those are our 4 bins, kind of in descending order of privacy protections. On the left here are our results. We have randomization type, which is whether or not the randomization is consistent. On the right, we have the scheme, which is the bitwise structure. So you can sort of see some of these schemes only appear in by certain manufacturers. DAA19 is kind of spread around. That's that dark green. 46-bit is the emerging consensus. That's sort of concentrated on the top. And always, of course, for Apple devices. And then the yellow is sort of starting to disappear. And so actually the yellow on the right and the yellow on the left are the same, but the colors, the other colors are representing different things on the left and the right. And so you can actually see, for example, Motorola is only in Motorola and the purple O2 is only in Samsung. On the left, you can see the emerging sort of improvement towards always randomizing with a couple of stragglers maybe in 2019. But if you go back to 2018, 2017, devices released then, you see all sorts of sort of mixed weird behavior. We're getting towards consistent randomization for all devices, but not quite there yet. Maybe, maybe now in 2021. So let's talk about some of the other features. Probe requests do not only include just a MAC address. They also include a variety of other features. I can't talk about all of them, but you can look at the ones that I'm missing in the paper if you're interested. But I'll talk about some of them that are interesting. And so sequence numbers are one. They're included in all probe requests. They are integers and supposed to be between 0 and 4095, but we notice that some devices actually stop at 2047, so they don't use that last bit. And traditionally they've been sequential because they're sequence numbers, so it's kind of in the name. But to protect privacy, they are now randomized in many devices. And the issue here is that if your device changes its random MAC address to a new random MAC address, but the sequence numbers are consistently increasing, then you can just trivially link the old MAC address and the new MAC address as belonging to the same address. It's the same device. So if you have sort of eyes on a device and you're watching it, you watch the changeover, then you can just link the two trivially. So this is bad for location privacy, and luckily, as it turns out, it is no longer really an issue because manufacturers have fixed it. It is gone. One thing that's interesting to note here is these two graphs. We like the top one better than the bottom one. That's because the top one is hardware and the bottom one is software. So that's indicating that this problem cannot be fixed simply with an OS update. For a lot of these devices, you need a more modern device that can do it. The first one is RTS-CTS. RTS-CTS is an attack that was discovered in 2017 by our research group. And in RTS-CTS, the premise of it is that devices, even when they're sending sort of random probe requests, if you send a message to their hardware address, they'll still respond to their hardware address, even though they're sending out random probe requests. So that frame that you send them is called an RTS frame, request to send. It's a control frame. So you can use this to sort of confirm or deny the presence of a device if you already know its hardware address. And so in 2017, all tested devices were vulnerable. So we wanted to know if it was fixed. Second attack that we looked at was 2016. ANQP is the Access Network Query Protocol, and it is designed to sort of allow devices to query access points and ask them questions about some services they have, usually for sort of inner working or offloading onto Wi-Fi or something like that. And this can reveal the hardware address, as it turns out. So let's see how that works. A device is sending probe requests out with a random address, and then a access point comes along and sends out a beacon that says, hey, I support ANQP. And the device goes, hey, I love ANQP so much that I will enter the action state. Right? So any action state behaviors that we talked about, like if some devices will start sending their hardware address in their probe requests instead of the random address. And what's supposed to happen now is the device should send an ANQP request with a random address because it's sending probe requests with the random address. But we noticed, and has been noticed before, that some devices will actually send this ANQP request with the hardware address, sort of defeating randomization. And so we noticed this still happens. Not on all devices, but in some modern devices, 2019 devices, this is a hardware year on the y-axis here. And a lot of these 2019 devices, ANQP, still vulnerable, depends on the manufacturer mostly, and RTS, CTS, still vulnerable for some manufacturers as well. So everything that I've talked about up to this point has been about what we call pre-association randomization. But the moment your device sees an SSID it recognizes, it will try to associate to that SSID, usually. And the first attempt that it makes to associate, that first frame that it sends, does not use a random address, because during the association process, you have to have the same address. So traditionally, it's used the device hardware address. So your device can be sending random addresses and be very good at protecting your privacy, but the moment it thinks it sees an SSID that you've connected to before, then it's going to immediately just start sort of sending out your hardware address. And so that is what we call post-association. And until iOS 14 and Android 10, which are reasonably recent, sort of last year, all devices used their hardware address when they associated and when they tried to associate. And so that's no longer the case in these modern operating systems. So let's talk about that. These devices implement what's called a connection-specific strategy. So what they do is when they go to a particular saved connection on the device, that connection has a MAC address associated with it. And when you go to connect to that particular one, you keep that MAC address. And then new SSID, I make a new connection to a new access point, a new address. So the idea is I'll have a specific MAC address that's persistent for my home, but when I go to the cafe, I have a different MAC address. So while you'll be able to tell that I'm at home, you won't be able to tell that it's the same device at home and at the cafe, because the MAC addresses are different from each other. So this presents some vulnerabilities. Adversaries can still track devices that return to the same location, and we all as human beings return to the same location quite a bit. And it also doesn't really help with big networks, so like EduRoam or municipal Wi-Fi networks. You can follow somebody around a big network if they're constantly associated to the same access, same connection. And finally, you can also just fake one of these. So if you know a device has a particular SSID loaded and you know that connection-specific address, then you can just sort of pretend to be that connection. The device will try to associate with you. You'll still get the device's connection persistent address because the first attempt that it sends will give you the connection-specific address. So let's look at the summary here. So all of these are the modern devices that we looked at. So they were released 2018 or later, and their operating system was released in 2018 or later. And you can see some pretty clear trends. The random addresses in probe requests are pretty much consistent, except for that one little outlier there. A generic signature, which I didn't really get a chance to talk about, but it is a characterization of the information elements associated with the probe request that sort of tell a access point's information about the querying device and will allow you to sort of bin a device and say, well, this probe request came from an iPhone 7 or something like that. Mostly no devices protect against this. They don't protect privacy in this way. Though there have been some attempts, and that's discussed in the paper. Most devices have a random sequence number now. ANQP and RTS, so these active attacks, are a bit of a mixed bag. Some devices still vulnerable, some not, depends on the manufacturer. And there's been marked improvement. And post-association is almost entirely based on operating system. So if you have a device that's Android 10, you have an iOS 14 or higher device, it's going to be doing post-association almost certainly. And then if you don't, then it won't. With that, I will thank you for listening to this presentation and ask if you have any questions.